Good morning, everyone. Am I audible? Okay. Are you able to unmute and speak? Okay. Please let me change the settings. Yeah. So I've allowed mic for everyone. Can you check now?
Yeah, it's fine.
Thank you. Okay. Yeah. Please be a bit careful if you are unmuted. Sometimes it might happen. It will disturb the class. But other than that, it is a very useful option which you will get to interact. But yeah, please be a bit careful. Okay, we will start in 2 minutes. I think we'll let others join. Okay, in 2 minutes we will take off. Yeah, okay. So let us start. I hope my screen is visible. Are you able to see my screen? Okay, thank you. Right, so let us start off with the course. So this is the course handout. Okay, so the course title is Analog IC Design. And the course number, I think we are following this one, VLMZG632. Okay. And this group, I think, falls under NSP 4, non-specific 4. Okay. And this has been being taught by Professor Sanjay Vidyadharan sir. So he is a Bitsville faculty. And I am Gautam. I am an adjunct faculty at Bitsville. So I'll be teaching you analog IC design for this semester. So I have my master's and PhD from BITS Hyderabad campus. So my topic was in microelectronics and VLSI. So you will be wherever there are some VLSI related courses. I think I will be one of the faculty members. And yeah, so these are the course objectives. Okay, so the first course objective is to get familiar with MOSFET structure, operation, and its modeling. Okay, and then we have single stage amplifier, differential amplifiers, and current mirrors. Okay, so this forms the first half of our course. Okay, so typically the course runs for 16 weeks. I think all of you are aware or that kind of what do you say training or that initial training would have been done. But anyways, so after 8 weeks, typically you have a mid exam. Okay, and after 16 weeks, we have something called as a comprehensive exam. Okay, so this is the structure, and each theory class that we meet for is 2 hours. So total 16 into 2, 32 contact hours. And parallelly, we have lab also. The lab will be based on cadence. Okay. So typically 5 to 6 lab sessions are scheduled. Okay. Again, it depends on several other factors, but either it is 5 or 6 depending on the kind of timetabling and other adjustments that we make. Okay. So the lab will be taught by Mr. Naveen Kanuri. So he is the lab faculty. So uh, again, if he is not available, again I might come in his place and teach the lab also. Okay. So yeah, so it is a 5 credit course. So based on uh, the number of credits that are required for the eligibility of your MTech degree. Okay, so this is a partial requirement, so it gives you 5. So typically 4 or 5 credit courses, they come with labs. Okay, and typically all the MTech courses are either 4 credit or 5 credit courses. So you can expect all your courses to have a lab component. Okay, so yeah, so typically labs start from after 3 weeks of the start of the theory classes, so that at least some portion of theory is covered, so that the lab can start. So the lab, as I told you, is based on cadence and LT spice also. Okay, cadence, we have around 40 to 50 licenses. So during the lab class, how to book a slot for cadence and everything will be explained by the lab faculty. So other than that, LT Spice you can install at your end and you can do the simulations on your own machine. So we will see in the second half of the class today, we will see that too. Okay. And this is the textbook that we are going to follow, Behzad Razavi. I think this is a standard textbook for analog IC design, whoever does that. So this is a very standard textbook, and this professor's lectures are available on YouTube also. I think the channel name is Long Kong. Okay, Long Long, Kong Kong. Okay, Long Kong, I think he's one of his students. So he records professor and he uploads all the lectures. So you can go to YouTube and search for Long Kong and Behzad Razavi. So you'll get professor's lectures also. They are excellent source of information. Apart from the textbook is also very well written. And apart from that, I think most of you know IIT Madras has a very good analog IC team. Okay, so Professor Shanti Pawan and Professor Nagendra Krishnapura. So these two professors have excellent lectures on analog IC design. They are available on NPTEL, and they are also available on their own course pages. You can simply Google them. Shanti Pavan, Professor Shanti Pavan and Professor Nagendra Krishnapura. Yeah. So these two professors, they explain in a very clear manner. Okay, and Professor Razavi YouTube lectures. These are also an excellent source. So apart from this textbook, and from time to time, we'll be referring to the Baker textbook also. Why? Because Professor Baker has his own website, cmosedu.com, where he uploads all the spice files, whatever he used to design his textbook. Okay, on the website you can download either the cadence files or the LT spice files that are required, and as you read through the textbook, you can perform the simulation and get a better understanding. So this is also an excellent source. Professor Jacob Baker's textbook, and these are all very standard textbooks. Alan Holberg is a standard textbook, and Ken Martin is also a standard textbook. Okay, and Gregorian and Teams. So this is also a standard one, but it is a little old. But anyways, all these are the standard textbooks and reference books. Okay, so this is our syllabus. Okay, so like I told, this is the first half of the syllabus, first 8 sessions or the first 8 contact hours. Okay, so this is today's class. So it is going to be introduction to analog. Okay, so like we see MOSFET structure, IV characteristics, and second order effects. I will push it to the second class. And but today, in the second half, like I gave in the message yesterday, we will concentrate on LT spice so that you can perform experiments or simulations at your end for better understanding. Okay, so then we start with single stage amplifiers, differential amplifiers, and current mirrors. Okay, in the differential amplifiers, of course, we have common mode response, so we'll be covering that as well, and analysis of differential amplifiers. So, in a nutshell, if you want me to say, the first half of the course is like this, where it is like introduction to MOSFET and second order effects. So that is one part. Single stage amplifiers and its analysis is second part. Differential amplifiers and its analysis second part is the third part, and current mirrors is the fourth part. Okay. So the current mirrors and the differential amplifiers go hand in hand. Okay. So that's why initially we start with the differential amplifier, then we move to current mirror, then we put the focus back on differential amplifiers. So you will see why that small deviation into current mirrors and then again back to differential amplifier. You might get a small doubt there. But once we start the discussions, it will be very clear. And then the eighth session before the last one before the exam, okay, is given for review. Or if there are any topics that are being spilled over, okay, sometimes some topics might be spilled over, right? So we can use this eighth session before the exam for covering any spilled over topics or as a more or less as a preparatory session as well. Okay, so that is first half of the course. After 8 weeks, you'll have your EC2 evaluation component 2 mid exam. So I'll explain what is EC1, EC2, EC3. Okay. So then we have the second half of the course, 9 to 16. You can see the frequency response. So you might be wondering in the first half, the most of the focus lies on the small signal analysis and large signal analysis, the DC analysis and the AC analysis. So we don't really talk about the parasitic capacitors and their what do you say effect on the overall transfer function. So that is reserved for the second half. Okay. So the frequency response of single stage amplifiers and differential amplifiers is occupying 3 contact hours. Okay. And then we go to the feedback amplifiers, identify different kinds of feedback. Okay. Current series, voltage, and so there are 4 types of feedback. So we'll try to understand all those. So then we move into op amps. Okay. So first one is the single stage op amp. Then we have the 2 stage op amps, then some gain boosting techniques. So in the 2 stage op amp itself, we'll have a lot of topics like frequency compensation and gain margins, phase margins. So we delve into a lot of control systems topics as well. And then finally, 16, before we go to the exam, we have some a review class, or this can be used for any topics that spill over. Okay. And let me show you the lab topics. So like I told, typically labs are 5 to 6 Okay, so out of this, any five experiments will be performed depending on the lab faculty, so how they want to take it forward. Okay, so this is the overall evaluation scheme. Okay, so it has three components: EC1 evaluation component. EC stands for evaluation component. So EC1, EC2, and EC3. Okay, so evaluation component one is like your daily evaluation. But these EC2 and EC3 are exams where you go to a center, sit and write the exam. But EC1 is you can do it from your home. It is completely online. Okay. So totally EC1 has 30% weightage. EC2 has 30% weightage, like you can see over here, and EC3 is the final exam, which is open book, so which has 40% weightage, so total 100% weightage. Again, in this EC1, that 50% is divided into 15 plus 15, you can see. So this 15 is typically given to the labs. Like I told, there are 5 to 6 contact hours for labs, so that is why half of the EC1 is given to labs. So this 15% is again divided like each experiment, 5 lab experiments, right? So each experiment is 2 marks. So 5 into 2, 10%. The other 5% will be for exam. Okay, so there will be lab exam and it will be online exam only. You need not go to any center and attempt the exam. So it is not like EC2 or EC3 where you have to go to a center and perform the or give the exam. So this lab exam, so lab assignment plus lab exam, these are completely online. Okay, so that is half of EC1, which is 30 divided by 2, which is 15%. So the other 15% is in my hand, which is given as quiz 1 for 5% and quiz 2 for 5%. So quiz 1 and quiz 2 will be conducted on Takshila portal. So do all of you have access to the Taxila portal, and have you logged in and checked whether you are in that particular course shell or not? Or is the training given to you how to access the Taxila portal, everything like that? Anything like that? Can one of you confirm if the training has been given, how to log
Yes, we
into the?
have the training.
Okay, okay, great. So then the last 5% is like a situated learning. Okay. So this is like a small project. So that is why I'm insisting on LT Spice so that you need not wait for the cadence licenses always, because that we have limited licenses, although good number of licenses, but the class strength is also more. So we push towards LT Spice. Of course, all these lab assignments completely are based on cadence. Anyways, that lab faculty will explain you neatly how this 15% is given. Okay. So typically, like I told, 5 to 6 lab sessions. Each lab session occurs once in a fortnight. Okay. So if there is a lab session occurring on May 1st, and the next session will be having 2 weeks gap, so it will occur again on May 15th. Okay, so in that way, labs will be planned. I think 2 labs will be planned before the lab exam, and 3 labs will be planned after the mid exam. Okay, and 3 lab sessions will be performed after the mid exam, and usually lab exam ends before the comprehensive exam itself. Okay, so before 1 week or 10 days before the comprehensive exam, the lab exam also ends. Okay, so this is the evaluation plan where your marks and what is the percentage of each of these components. Okay. So, and like I told, so all the materials will be dispersed in teams. So in our teams, mm, okay, somebody gave something already. Okay, oh, you changed the name and gave it. Okay, fine. Anyways, So this is our course shell or whatever in the Microsoft Teams. So in the general, there will be two channels. Once the lab schedule comes out, there will be lab channel also. So there you will be interacting with your lab faculty. So in this general channel, we will be having our interaction. So whatever I want to convey, so like this message, I'll be posting here. Okay, in this general tab. Okay. So if you see here in the general tab, there are again three sub tab. One is for posts. Okay, so this is the post, and one is the shared. Okay, so in the share tab, so this is where we will be, or I will be giving out the general course content. Okay, and mm, no, it's not opening because, yeah. So see, you can see the class materials. Once this class is done, there will be another folder here called recordings. Okay, so in that recordings, you will have the compressed version of our 2 hour class recording, so which will be available to you for like the rest of your course duration over here. So you need not worry about any missed class or anything like that. You may revisit the recording any number of times. And in this class materials, I have already given two things. One is this course handout. So you can access the course handout. And second thing is I created a folder called LT Spice related. Okay, so we'll be working on this TSMC 180 nanometer model file. So the model file and the symbols are zipped in this and then uploaded here. Okay, when we come to the second half of the class where we discuss the LT Spice, I'll show you what to do with this. Yeah. And then this is the first and preferred way of communication. Okay, so where in posts, I'll be dispersing information in the form of post in Microsoft Teams. If you want to ping me, you can ping me on Teams on the personal window. Okay, typically I respond if it is within the morning hours, but yeah, sometimes students ping in the night, but you cannot expect a immediate response. But if it is in the morning business hours, I typically respond to whatever are the doubts or whatever clarifications that you need. So this is one way with which we'll be communicating. And the second way, of course, is our Takshila portal. Okay, so this is our core shell. I think if you look at participants, see this is a faculty login. So it might not, you might not have all these options, but I think I can already see some names that are matching. So this is our course. Okay, so if there are any announcements, like I told, the announcements will be made in Takshila portal as well as in the Teams, the general tab. Okay, so I'll be putting in the announcements as well. Okay, and then there is a discussion forum. If you want to initiate something, I think everyone will have access to this. You can start the discussion forum. Okay. So this is like I told the instructor login. So typically, if you log into course, if it is something showing as hidden from students in my login, you won't be able to see all this. You might be only be able to see until here past question papers. But yeah, like I told, quiz one, quiz two that I told will be updated here. Okay, once I update, so I'll put a message in the announcement and in Teams also, so that nobody loses out on the information. So again, lab assignment 1, 2, here only 2 are given, but like I told, 5 contact hours will be there. So it will go up to lab assignment 3, 4, 5 as well. And assignment 1, I'll be using it for situated assignment. And we'll have only 2 quizzes, quiz 1 and quiz 2. Okay. So this is where quizzes, assignments, and lab assignments will be conducted in the Takshila portal. So typically each lab assignment will be given 15 days. Like I told, you have 15 days gap between two lab sessions, right? In those 15 days, you have to complete the lab tasks. I think it won't take you more than half an hour, 40 minutes, whatever lab task is given by the instructor. So you have to finish it and then upload it as an assignment. So quiz will be like MCQ based. So once I enable the quiz, once I upload the questions and enable the quiz, you can get to, you'll get those questions in a sequence and you have to answer them. And like I told, it is out of 5 marks. Each quiz, quiz one, quiz two, both are out of 5 marks. And typically, I will also announce when the quizzes are being updated. So all the information will be given. So you need not worry that I might enable the quiz suddenly and ask you to comply. Okay, so both quizzes, all the quizzes, lab assignments and assignments are completely online. Even the lab exam is also online. Okay, so these are the two important things that we'll be using. One is the Teams, our course shell, and this is Takshila portal. Again, this is our course shell. Analog IC design S225 VLMCLZ ZG632. Okay, so we'll be using this. Okay, so any doubts so far? Link for Takshila. So this is like single sign on, if I'm right. I think whatever sign in credentials that you use for Teams, you'll use the same for the Takshila and any other portal that comes your way. Okay. So you'll have access to a lot of other tools like I think all of you will get access to MATLAB. Okay. So everything is this single sign on. If I'm using the correct word, I think I'm using the correct word. So the same credentials are used. Whatever are the credentials that you used now to log into the Teams, those same credentials can be used for the Takshila portal and any other tools that you might have access to. Okay. Any doubts so far? Shall we start off with the subject? Any doubts in the evaluation components and yeah, no doubts. Okay, fine.
Sure, I have one question.
Yeah, please, please.
So, what is that 320 structure of that credentials?
Um, so typically,
So
if it is, what do you say, not an online course and if it is an offline course, like it typically happens in, what do you say, other, like your BTech course. So this usually stands for the contact hours. Okay, so this is called LPT. Okay, so L stands for lecture, P stands for practical, and T stands for tutorial. Okay. So this actually means you will have 3 contact hours of lectures per week and 2 contact hours of practicals per week. So total 5 contact hours per week. Okay, so this typically makes sense if it is what do you say, an offline course. But this is the typical breakup for offline courses. Okay, but like I told, we'll be having 16 16 sessions, each session being 2 hours. So 16 into 2, 32 contact hours and 12 lab hours. Okay, so total around I think 44, 32 plus 12 is 44. 44 contact hours is what we'll be looking at. So this is called LTP or LPT structure. So depends on which university and which jargon you are using. Okay. So weekly, three contact hours for lectures and 2 contact hours for practical. So that is the breakup that it is trying to convey. But this is being an online course. Okay, it doesn't make that much sense because we are trying to put everything in the weekend, Saturday and Sunday, all the labs and theory. Okay. But yeah, so this is the typical nomenclature followed by all the universities. Is that clear? That might create some misunderstanding, but yeah. That,
Yeah, one more
that is,
thing, Professor. So that one, standard books, those things. Is there any standard website to download all those things?
website, like I told, Jacob Becker has his own website, cmosedu.com. Okay. Yeah. So here you can find, see if I go to LT Spice. Okay. So here he gives you all the LT Spice cmosedu.zip. Okay. So whatever is the circuit that professor is discussing in the textbook, so that circuit will be available in that zip folder. It will help you with understanding. So this is one good source. Okay. So they even have so many other MATLAB, Mentor, and Cadence. Cadence also they have. Okay. So you can have a look at it. Okay. So cmosedu.com. It is very famous. So if you have these textbooks, so you can, as you read through the textbooks, so suppose chapter one, circuit figure number 1.20, you will get the same order in this zip folder also. If you go and simulate it, you can try and understand the concept better. It is like an aid to the textbook. And it won't replace the textbook, but add you as you read through the textbook, it will give you these LT Spice simulation files will give you much better understanding. So this is one source that I can say. And like I told, Professor Razavi's lectures, Long Kong, by the name of Long Kong, in YouTube, and NPTEL video lectures of Professor Nagendra Krishnapura and Professor Shanti Pawan. These are ultimate sources of analog IC design video lectures. So nothing can beat those lectures. So Professor Razavi and Professor Nagendra, Professor Shanti Pawan. So if we follow those, I think you'll be an expert in analog. Yeah, right. Anything else?
Oh no, thank you.
Okay, right. So let us start. So let us start off with the course. So typically, I like to, what do you say, write down and explain, try to explain the things as I speak. Okay, so that is the thing I follow. And after the lecture is done, I try to upload the slides of the same. Of course, the slides won't be as descriptive as the class. The slides will be like it rather presents focus, okay, on a particular topic. But if you want much more depth and clarity on the topic, you can refer to these notes. Okay, so once the class is done, I convert these notes into PDF and upload into our material section as well. Like I told, after the class, I'll give the PDF or the PPT of this as well. But like I told, the objective of the PPT is to show you the overall path. But if you want more and more details and more clarity, I think you can check the notes and any other material that I might give as we go along. So that is one distinction I want to make. I don't want to overload all the material or all the derivations that I try to do here into the slides. Okay. But yeah, you will be allowed to carry both the slides and the class notes that I disperse over here. Okay. So for your open book exam, you need not worry for that. Okay. Right. So yeah, where do we start? I think is a very good point is why do we have to study analog IC design? Okay, so why not digital? Okay. So anyone, why this subject? Why analog and why not digital? And what is the distinction between these two? Okay, right. So whatever are the real world signals that you find, okay, so are completely analog in nature. Okay, so the text that I'm speaking, the voice that is coming out, okay, and if you take any real-time signal and if you try to plot it, so everything is analog. When I say analog, I can also say that it is continuous in time and amplitude. Okay, so the typical examples are whatever are the sensors readings. So all are continuous time and continuous amplitude. Okay, so a typical sensor can be an ECG sensor. So it has the 12 lead. Okay, and you know the typical ECG, something like this. Some waveforms like this. Okay, it's very famous waveforms. They keep showing us in the movies. Okay, and the voice that I speak. Okay, so all these signals are the real world signals that come out, and all these are analog. By analog, I mean they are continuous in time and amplitude. Okay, of course, why do we have digital? Okay, so all the computation that we are enjoying today. Okay, so all the computation we are seeing wonders being created by AI and ML, the kinds of LLMs that we have, everything is made possible only because of the computation that has been made available to us in the last, let us say, from 1970s onwards. From 1970s onwards is where the VLSI revolution or the semiconductor revolution started, right? Even Intel released their first microprocessor 8008. Okay, so when the computation stone started rolling, okay, so we are able to do more and more complex tasks in less and less time. And we know the type of improvements happened to mankind in the last 50 years is exponential. And nowhere in human civilization, this kind of technical advancement has happened. Okay. And that is possible, that was made possible only because of the computation that we have available in the digital domain. Okay. So MIT, they give top 10 technologies every year. So uh, I think you can do a simple Google search, and then I think they are doing it from the year 2001. So till date also they have. So MIT review or something. So they release top 10 technologies of that particular year. And it is very evident that every year, whatever is the top 10 technologies from 2001, from since last 20-25 years. So all those technologies are directly dependent on the computation that is made available to us. Okay. So our real computation power is in the digital domain, but all the real world signals are in a continuous time domain. Okay, so this is where the analog IC design comes in. So it acts like an interface between the real world and the digital world, where we convert the given analog signals into digital domain. That might be a better introduction to an ADC based course, because ADC is the actual module that converts the continuous time and continuous amplitude signal into discrete time and discrete amplitude signals. But if you want to design and develop a state-of-the-art delta sigma ADC or a pipelined ADC or a successive approximation ADC, okay, so you need to have the basics of analog IC design, and that is what this course is trying to impart. Okay, so we'll be getting the basics of the analog. Okay, in analog, what are the typical types of problems that we face? So typically, what happens is all these signals are in millivolts range. Okay, and we know that these signals needs to be amplified. Okay, so most of the focus of our analog IC design course is on amplifiers. So you have seen, right, single stage amplifiers, differential amplifiers, that is forming the first half. Then in the second half, we have seen the frequency response of single stage amplifiers and the differential amplifiers. Okay, so you can say this majority of the course is focused on. So there are low magnitude sensory signals that are available in the real world. The world is full of them. So how do you take them in and amplify them? So that is going to be the motto of this course. But overall, if you want to go from analog to digital domain, okay, so first you need to amplify those signals, and then do something called sampling, and then after sampling something called quantization, and after quantization you go into the digital domain. Okay, so this is the gradual progression. So because we are still at the start, we are only at the signal conditioning. So by signal conditioning, I mean the real world signals are very low magnitude in nature, typically tens of millivolts or even microvolts for that matter. So EEG signals, the scalp electrodes that we see, so they are typically hundreds of microvolts in nature. EMG, electromyogram, so where the muscle movements come, so those are in microvolts in nature. So all these real world signals are continuous and they are very, very small. Okay, so how do you amplify them to a proper level so that I can later give it on to an ADC, which converts into the digital domain. Okay, so we are at the first block where we are sensing these millivolts, microvolts that are coming out of the sensors. And the first task we are trying to obtain or we are trying to do is how to amplify them. Okay, so that is going to be the focus of the course. Okay, so that is the why of your course. So and then if you might ask how we are going to do it. Of course, like I told, so the answer is silicon. Okay, so right. So I won't go deep into the physics. Okay, but a small. Okay, so how many valence electrons in silicon? How many valence electron? How many valence electrons in silicon? Four.
Four.
Okay, so
Sure, it's
silicon
four.
form, yeah, silicon forms bonds, right, with four of its neighbors. Okay, so these are the four valence electrons that I'm trying to convey with these dots over here. You might be wondering why I am putting so many dots, but these are the four valence electrons. So it forms a particular bond with the valence electron from the next atom. What type of bond is this? You would have done this in your 11th and 12th standard. What are the two? What are the two types of bonds? Ionic bonds and covalent bonds. Okay, so this is a covalent bond. Okay, so typically, yeah. So this four other atoms with four silicon forms these covalent bonds. Okay, so typically, so this forms a nice 3D lattice shape. Okay, so it is like a cube. Okay, and nicely these silicon atoms are nicely arranged in this lattice. This is called as a lattice. And with silicon forming nice covalent bonds in all directions. So this is called as a lattice or a crystal. Okay, so this is called as a crystal or a lattice. Okay, so what happens is because this crystal has a nice shape. Okay, so it is, what do you say, conducive for vibrations. Okay, so even in your real life also, you can see solids, they transfer vibrations more compared to a substance that doesn't have any form or shape, isn't it? So what happens is room temperatures, at room temperatures, so there will be some vibrations in the crystal because of this temperature. There will be some vibrations, and sometimes what happens is the covalent bond breaks. The covalent bond breaks, and the electron escapes the covalent bond. Okay. So this escaped electron is then available for conduction. Okay. This is available for conduction. So why am I worried about the electron? We know that electron carries a charge. Okay. And I know that rate of change of charge is nothing but what? What is rate of change of charge? dq
It's
by dt?
current. It's current.
Yeah. Yeah. So this is nothing but current. Okay. So I am more worried about my free electron. Why? Because if it is because it is carrying a charge and the rate of change of charge from one point in time to other point in time. Okay. So it results in a current. Okay. So this silicon that loses the electron, okay, so it is immobile. This silicon atom itself is not moving, but what is moving in the lattice? The electron that has escaped the covalent bond because of what? Because at room temperature, because this temperature causes some vibrations in the crystal, and this electron is free and it is free to move. Why am I worried about the free electron? Electron, carries a small amount of charge, minus 1.6 into 10 power minus 19 coulombs. All of us know that. And rate of change of charge is nothing but current. Okay. So that is why I am worried about the free electron. Okay. So typically we'll look at some numbers. We'll be looking at some numbers. Typically, there are around 10 power 25 atoms per centimeter cube. Okay. So typically in a silicon crystal, okay. So if you take a centimeter cube, so this is nothing but a volume. So if you take a small volume, small cube, okay. So in this small cube, okay. So you'll find 10 power 25 silicon atoms per that centimeter cube volume. Okay. So this is like a room, and in that room, I'll be finding 10 power 25 silicon atoms. And like I told, at room temperature, what is the number of free electrons? Can anybody take a guess?
Sir, 10 to the power 10, I guess.
So anywhere between 10 power 10
To
to
15, I
10
guess.
power 11. Some textbooks say 10 power 15 also, which is a low number. Is it a high number?
It's a low
Is
number,
it?
sir. It's not good for conduction, I guess.
It is not at all good for conduction, because where is 10 power 25 and 10 power 10? So it is like 15 orders of magnitude, right? So you are comparing, you think in terms of rupees, okay? 10 power 10 rupees and 10 power 25 rupees. Okay, there is no comparison. Okay, right. So in order to improve the number of electrons, what we do? Now the question is, how do I increase the number of charge carriers?
Uh, by using external source.
Yeah. Okay. So this process of introducing external sources to improve charge carriers, what is it called?
Doping, I guess. Doping.
Doping. Yeah. So this is called as doping. So typically, what do we dope with? You want more number of electrons. So I know that phosphorus is an atom that has how many electrons in its valence band? 5. Okay, so it is a pentavalent atom. Phosphorus belongs to pentavalent. Okay, fifth group in the atomic table. So it has 5 valence electrons. Okay, so I'll be typically introducing how many? Okay, so somewhere between 10 power 15 to 10 power 16 phosphorus atoms per centimeter cube. Okay, so what happens is this phosphorus atoms with its 4 valence electrons, it forms bonds with the silicon atoms that are already present in the lattice. Okay, but what about the fifth electron? The fifth electron is free to move, so it moves on into the lattice and it is available for conduction. Okay, since this phosphorus lost 1 electron, so what is the net charge on this? So it lost 1 electron. So what is the amount? So it is positively charged. Okay. So it becomes phosphorus ion. Okay. So when I say phosphorus ion, it is nothing but P plus. Okay. When it is phosphorus ion, it is P plus. Okay. So is it immobile or mobile? So it is nicely present in the lattice with 4 other silicons, right? So is this positive charge, positively charged phosphorus available for conduction? That is my question. So if it is available for conduction, it has to be mobile. Okay. Only when the charges move, current follows. Okay. So is this positive charge moving in the crystal? That is my question. So is it mobile or immobile?
It's mobile, sir, I guess.
No, it is immobile. So it is
Okay.
nicely stuck with all the silicon atoms, right? So it has 4 covalent bonds and it lost its 1 electron. Okay. Unless because of some thermal vibration, it is losing another electron. So there are 3 other atoms as well. Okay. So this phosphorus ion is immobile. It is in the lattice and it is not available for conduction. But because it is losing one of these electrons, okay, so this is available for conduction. Now, if I am adding 10 power 15 atoms per centimeter cube of phosphorus, how many free electrons do I have now? How many free electrons I am adding?
Number 15.
10 raised
Yeah,
to the power
yeah,
15.
yeah. So I'll have 10 power 15 electrons per centimeter cube that are also added. But for that, there is somebody wants to come. I don't know, yeah, but you have to log in with bits login ID because sometimes some. Okay, anyways, yeah. So because we added 10 power 15 atoms per centimeter cube of phosphorus, okay, so we'll be having 10 power 15 electrons per centimeter cube. But for that, what should happen is all these 10 power 15 phosphorus atoms should be ionized. Okay, so that means all these 10 power 15 atoms, they form bonds with silicon. Okay, so that is what we are trying to say. So that is when we say I'll get all these 10 power 15 electrons. Okay, only if all the phosphorus atoms are ionized. Okay. Anyways, that is not the point of discussion over here. Uh, right. So now we have more number of electrons. So what will be the total number of electrons at room temperature? So previously we have 10 power 10 plus now we'll have around 10 power 15. So I can roughly call this as 10 power 15, right? See, there is 5 orders of magnitude of difference. See, I have 1 rupee, I have 1 lakh rupees. See, this is 10 power 0 and 10 power 5, right? Okay, so 6 orders of magnitude. So 1 rupee and 1 lakh rupee. I cannot say that I have, or usually we don't say that I have 1 lakh 1 rupee, right? So we nicely approximate it with the higher order of magnitude. So we can, of course, there are electrons that are released due to the temperature disturbances in the crystal, but the number of free electrons that are in the crystal due to ionization of the pentavalent impurity that is given into the silicon, that is 5 orders of magnitude more. Okay, and that is why we typically say I have 10 power 15 electrons in the lattice, which is available for conduction. Then this is a good number, and this typically is will give us good number of charge carriers that result in a current flow. Okay. Anyways, I will stop my physics class here. Okay. So, like I told, if you go to Professor Rajavi's lectures, there will be more and more details. Okay. So, if you are interested, two things are very important. So, one is law of mass action. Again, I don't want to go in detail in the class over here. Okay. And Maxwell-Boltzmann equation. So these two expressions you can study. Okay. So you'll get more insight into what is happening in the lattice. Okay. So this relates electrons and holes. Okay. Right. And this relates voltage difference between 2 points in a crystal because of different charge concentrations. Again, too much physics that would be coming into this at this point. So, but what this is trying to do is in the crystal, so this is the crystal, this point has some charge concentration, so n number of electrons, n1, and another point has n2 number of electrons. Okay, so there will be a potential difference between these two. Okay, so that will be given by this Maxwell-Boltzmann equation, which will be a function of these two, n1 and n2. So how it relates and what are the origins? Okay, so you should also, if you are interested, Poisson's equation and law of continuity. Again, too much physics because this is not a physics course, but you can explore these two as well. So you might get more insights into the behavior of the electrons in the crystal. Yeah, right. So moving on. So because we introduced the atoms, what we called as doping. So if we introduce the pentavalent atom, okay, so we get more number of electrons. Similarly, if we do the same doping with a trivalent atom, okay, so we get something called more number of holes. Okay, so the example being boron. So boron has only 3 over here. Okay, so again, it also forms bonds. Okay, and sometimes what happens is because of the thermal vibrations. Okay, so there will be a silicon over here. Okay, a free electron might come and sit over here and complete the bond. Okay, and after some amount of time, so this might be freed and it would have moved into some other location. Okay, so in effect, what happens is you feel like a positive charge has moved from this location to this location. So that is nothing but hole. In reality, hole is not present. It is nothing but the movement of charge visualized in a reverse fashion. That's it. Okay. So there are some open covalent bonds that are present. Okay. So your electron goes and sits there at point of time T1. At the point of time T2, it goes and occupies some other location. So this movement in effect, what it looks like is a positive charge has moved from this P2 to P1. So this is nothing but considered as a hole. Okay. And this is made possible by trivalent atoms, and these are called as majority carriers. Okay. So if the majority carriers are electrons, we call it an N-type semiconductor. And if the majority carriers are holes, we call it a P-type semiconductor. Okay. Yes, we'll go ahead with the concept of Moss capacitor. Okay, so why silicon? So I'll give more reasons why silicon is taken over here when we discuss the Moss capacitor. So suppose I take three layers, one a metal, okay, and one an oxide. Okay, so let me. Hmm. And another thing, another layer is nothing but semiconductor. Okay, so this is MOS. When I say MOS capacitor, so M in that MOS stands for metal, O for oxide, and S for semiconductor. Okay, suppose I have taken the P-type semiconductor and I know that holes are majority carriers. Okay, so when I said oxide, what is this semiconductor made of? This P-type semiconductor, what is typically made up of? Made out of silicon, and this oxide is nothing but silicon dioxide SiO2. Okay, so that is why silicon is preferred. Why? Because there is a lot of compatibility between Si and SiO2 interfaces. Okay, so this point is called Si-SiO2 interface. And so this is formed, this silicon dioxide is formed by oxidation of silicon. Oxidation means you expose it to oxidation. So you take it in some vacuum chamber and expose it to oxidation. What happens is SiO2 layer is formed. Okay. So like I told, so this interface is has a lot of compatibility. Why? Because Si and SiO2 are formed easily with the help of oxidation. So that is one of the reasons why silicon is preferred, because this oxide is a natural progression from silicon and it can be easily obtained with the help of oxidation. That is also one of the reasons why we go ahead with silicon. Okay, right. So this is a MOS capacitor. Okay, so let me call this terminal as bulk or body. Okay, so when I say bulk, this is the semiconductor terminal. Okay, and I have another contact over here. Okay, which is the metal contact. And I take these two and I apply some potential. So let me call this VGB. So this metal terminal, I am calling it as gate. And this semiconductor terminal, I am calling it as bulk or body. Okay, bulk or body. And then there is an oxide insulator that is separating these two. Okay, so can I call this a parallel plate capacitor? Yes or no? So this is this is acting as the top plate of the capacitor, the metal, and the semiconductor or the bulk or body is acting as the bottom plate of the capacitor. And then there is a dielectric, which is nothing but an insulating material. Silicon dioxide is an insulating material which is acting as a dielectric between these two plates. So can I say that this is nothing but a capacitor, a parallel plate capacitor? Can I say that? Okay, so that is why this is called as a MOS capacitor. So this terminal I am referring it to as the gate terminal, and this terminal I am referring to as the bulk or the body terminal. Okay, now let us apply some voltage. Let us apply some voltage and then see how this responds. Okay, right. So I'll take this MOS capacitor. So let me draw again and then I'll. Maybe I am exaggerating this oxide thickness a little only for understanding purposes, but typically in a MOSFET, that is a very thin layer. This is nothing but body. This is nothing but gate. This is my metal. This is my oxide. This is my semiconductor. So I told you that this is a P-type semiconductor. And case one, what we are going to discuss is I apply a small negative voltage. That means VGB is less than 0. Okay, so this is my VGB voltage source. Okay, sorry. So I am applying a small negative voltage. So what will happen? Okay, so what charge will be deposited on this plate? What charge will be deposited on this plate? So there will be some negative charge forming in this plate. Yes or no? Yes or no? Okay, right. So I told you that this is a P-type semiconductor. So what are the majority carriers in this P-type semiconductor?
Positive. False.
Okay, so these are called as holes, yes or no? So, so this negative charge, what will it do to these holes? This negative charge, what will it do to these holes?
It
So it
makes
will,
to flow the charges to the holes.
okay, so it will attract those charges. So it will attract the holes near to the interface. So this is my silicon dioxide interface. This is where the action is happening. Okay. So I am worried about whatever is happening here. Okay, right. So when I apply a small negative voltage, okay, what is happening? A negative charge is applied to this plate of the capacitor, which is my metal. So this attracts the positive charges or the holes that are present in the p-type semiconductor, because p-type semiconductor majority carriers are holes. Okay, so these holes, these majority carriers, they come and stick to the interface. Okay, so this is called as what? This is called as accumulation. Okay, so the positive charges that are present or the holes that are majority carriers in the semiconductor, they are attracted to the interface now. Okay, this phenomenon is called as accumulation. Okay, right. So let me go to case 2. So let me copy paste this one. So what will I do now? What will my case 2 be? I'll apply a small positive voltage now. Right, tell me. So because this is a positive voltage, what will happen to this? So there will be some positive charges deposited on this plate of the capacitor. Right. So what will happen here? Tell me, what will happen at the interface now? Previously, we have seen that the majority carriers, that is nothing but the holes, they came and sat at the SiSiO2 interface. Okay, what will happen now when VGB is more? For a small positive voltage, what do you think might happen? Yeah, you can take a guess. Yeah, what do you think it might do? So these are positive charges, and there are positive charges in majority over here. What will happen? Like poles repel and opposite poles attract. Okay, and this is a positive charge. There is an abundance of positive charges over here. So what might happen? What might happen?
Act as a resistor.
Sorry.
Repulsion.
Yeah. So like I told, like poles repel, right? So there is a positive charge that is being applied because of this voltage source over here, and this has an abundance of positive charges. So what happens is these positive charges are repelled from the interface. Okay, so they move away from the interface. I am worried only about what is happening at the interface. Okay, so what happens is because it is repelled, this interface is devoid of any charges. This interface is devoid of any charges. Okay, so this condition is called as depletion. This condition is called as depletion. Okay, right. So what happens if I increase VGB more? What happens if I increase VGB more? So let me go to the next page. So case 3, VGB is positive and much higher. Okay, so let me copy paste that. Right. So now tell me. So what are these charges? These are positive charges. So what will happen at the interface? Remember, what are the minority carriers? Yeah, what are the minority carriers here?
Electrons.
Okay, so what is the net amount of charge on electrons? Electrons are negatively charged or positively charged?
Negative.
Negative.
Negatively
Negatively.
charged. So this positive charge, what will it do to the electrons? What will it do to the electrons? It will attract them to
Attract
the
them.
interface.
Minority
Okay,
attract.
so it will attract these electrons to the interface. Okay, See, you cannot view these two as separate events. Like I told, I conveniently wrote that because these positive charges help them repel. At the same time, electrons are also being attracted. Okay. But this small positive voltage is not able to attract so many electrons over here. Some electrons which are in the vicinity of the interface, they are still getting attracted. Okay. Both events are happening. Okay. I conveniently made it look like both are separate events, but both are happening separately. So positive holes are being driven away from the interface, and the negatively charged electrons are also getting attracted. Okay. So now I'll make one bold statement. Okay. So follow this carefully. Now there occurs a voltage VGB for which, okay, the SiSiO2 interface. Okay. So this is the region that I'm trying to focus on. Okay. For which the SiSiO2 interface has become as negatively charged as it is positively charged in the bulk. Okay, so what I mean to say is, so at a point of voltage of VB, what happens is, okay, there are so many electrons that are present in at the interface, okay, and the concentration of electrons at the interface is so much that it is equal to the concentration of holes in the bulk. Does that make sense? Any sense? This is the statement that I made. So at a particular voltage, what is happening? The concentration of electrons at this interface is almost equal to the concentration of holes that is present in the p-type semiconductor. Okay. So this scenario is called as inversion. This exact scenario is called as inversion. So this became as negative, okay, as it is as positive inside the bulk. The bulk is p-type. P-type has majority carriers as holes. Okay, so there is some hole concentration that is present over here. Okay, what is happening at the interface because of this voltage? This voltage is causing, okay, the a rush of electrons to the interface, and so many electrons came and sat at the interface so that at this interface, the concentration of electrons is almost equal to the concentration of holes inside the bulk. Okay. So that point, what has occurred? What has occurred at that point? We say that inversion has occurred. And what is this voltage called as? What is this voltage called as? Anyone?
Threshold
What is this?
voltage.
Very good. So this is nothing but our good old threshold voltage. Okay. Right. So this is the MOS capacitor. Okay. So is there any current flow here? Is there any current flow here? This is a oxide layer is nothing but an insulating layer, isn't it? Okay. Silicon dioxide is nothing but quartz or glass, right? So it is a very good insulator. Okay. So it doesn't allow current to flow through it. Yes or no? Okay. So because of these voltages, okay, the gate voltage that I am applying over here, is there any current flow through the insulator? Is there any Ig that is flowing through the insulator? Is there any current flow because of this voltage? The capacitor is getting charged, okay, but there is no current. But there is no current, okay. So this is where we move to our MOS transistor theory. Okay, so this is where we move to our MOS transistor theory. Okay, so the mass capacitor is done. What are the three phenomenon that we studied? Can anyone quickly summarize me? What are the three phenomenon? When VGB is VGB is a less value, it is accumulation.
Zero it is accumulation. EGB
Yeah.
greater than zero depletion, and EGB is positive and much higher inversion.
Yeah. So quickly summarize. I'll put it this way. When VGB is less than zero, what is it?
Accumulation.
Accumulation. VGB is greater than zero. VGB is less than VTH.
Depletion.
Or I can put it this way also. So this is nothing but
Depletion.
depletion. And VGB is greater than VTH, I can say it is
Inversion.
right. So this is the quick summary of what do you say, a mass capacitor. Now we have seen that in this capacitor there is no current flow. Okay. And if I want to design an amplifier, current is of essence to me and it has to have certain characteristics. Okay. And because there is no current flow in this mass capacitor, it is not doing anything to me. Okay, so this is where I move to the next topic called as the MOS transistor. Okay, so I have the same gate. I have the same gate. I have the oxide. I have the semiconductor. Okay, right. So what else do I have now in the MOS transistor? What else do I have?
Source and drain.
So
Substrate.
I take another two regions of heavily doped. So this is my P substrate. So this is my gate.
Silicon region and gate.
This is oxide. This is semiconductor. Okay. Right. So what is happening? Electrons are coming here during inversion. Inversion is formed. Okay. So I take two N plus regions. What do I mean by N plus region?
N-type MOS.
Okay. So this is doped with N type. Okay. But why am I calling it plus? Why am I calling it? It is heavily doped. Okay. So what is the typical doping concentration we have seen? 10 power 15, right? So we have 10 power 15 electrons per centimeter cube. When I say heavily doped, in order to give you some quantity, so it is around 10 power 17, 10 power 18. So 2, 3 orders of magnitude higher. So I take two regions. Okay. So I call this region as source and this region as drain. Okay. So this is also full of electrons, heavily doped. This is full of electrons. Okay. And because of the mass capacitor, inversion has already occurred over here. And this is also full of electrons. Okay. In order for the current to flow. So initially I applied some voltage and the electric field was in this direction. Yes or no? Because the charges were getting accumulated here, the positive charge and negative charge were getting accumulated here, and we know that electric field can be represented as lines and they initiate from the positive charge, they end at the negative charge. Okay, so because of VGB, I am having an electric field, but it is in which direction? It is in vertical direction. So this results in a vertical field. Okay, now when I have this mass capacitor in depletion, and there are two sources of electrons that are present over here, and I apply a voltage between these two terminals, VD and VS. Okay, and then I apply a voltage between VD and VS. There it results in another electric field called as a lateral electric field. It results in another electric field called lateral electric field, and there will be electric field in this direction. And because there is a nice highway already, Okay, so this inversion is formed. Okay, there is an electric field and some electrons that are present in the source can now easily cross over into the drain, thereby forming the current because of the potential bit difference between these two terminals called as the drain and source. Okay, that will result in a current called as the ID for me. Okay, so if you take the MOS capacitor, I have only the vertical field. Okay, and I also have an insulator in between, and because of this, there is no current flow. Okay, now what am I leveraging? This MOS capacitor, I am putting it in inversion. Okay, and I apply what kind of electric field? A lateral electric field in this direction. And because of this inversion layer, which already has electrons, and the electrons are in majority in both source and drain, this acts as a channel for these electrons to cross over from source to drain. So when electrons are crossing over from source to drain, we say that a current is flowing from drain to source, okay, which is called as ID. Okay, so this forms the MOS, basic NMOS. This is the basic NMOS structure. Okay, so let me redraw it again. So NMOS transistor. Okay, what do I have? I have a substrate. What type of substrate do I have? P or N? An NMOS.
P type.
Yeah. And then I have two N plus regions. This is my P sub. My MOS capacitor has to be still to be there. So this is my oxide layer and this is my metal. Okay. So there are four terminals now. What are my four terminals? What did I call this as? So this is my source. This is my drain. This is my gate. What is the other terminal in the MOS capacitor? What was my second
Bulb.
terminal?
Bulb.
Bulb.
That is called body. Okay. So these are the four terminals that I have in the MOSFET. These are the four terminals that I have in the MOSFET. Okay. Right. So you can think of the MOSFET. Okay. It is a very simplistic explanation that I am trying to give. Okay. If you want me to follow the exact physics, whatever explanation that I am trying to give now, it won't make much sense. But hang on and follow for the intuition that I typically apply when I try to understand a MOSFET. Okay. Now, previously, I applied a positive voltage between gate and bulk. Yes or no? Okay. So now I'll apply two voltages. What are those two voltages? Yeah. What are the two voltages now? Anyone?
VGS and
Yeah. So between these two terminals, what is the voltage that I have? Between gate and source, what is the voltage that I have?
VGS.
VGS. Yes or no? This is VG, this is VS. Okay, this is VG, this is VD. So what will this be? VGD. Okay. And okay. In order to complete the circuit, what I am doing is I am connecting the source terminal to the bulk. I'm connecting the source terminal to the bulk. Okay. So here VGS is equivalent to what voltage in your MOS capacitor?
VGB.
Yes, exactly. So electrically equivalent, right? Source I directly connected to bulk. Yes or no? So can I say that VGS is equivalent to VGB from the mass capacitor?
Yes, sir.
Okay. And then there is another voltage also called as VGD. Okay. Right. So let me erase this because I need multiple copies of this figure. I need multiple copies of this figure. So yeah, right. Now case one, okay, VGS is equal to 0. Okay. Now tell me, see your source is now equivalent to bulk. When VGB was equal to 0, was there any channel formed? Was there any channel formed?
No.
No,
No.
sir.
So in this case, do we have any channel? VGS is nothing but VGB. Do we have any channel?
No.
No, sir.
Okay. No, there is no channel. Okay. When there is no channel, do we have any current flow? Is there any proper path for the electrons that are present in this drain and source to cross over? There is nothing. So what is your comment about the drain current? Will there be any current?
No.
No.
No, sir.
ID will also be equal to 0. Okay. Right. So let me go to case 2. Let me copy paste this one. Case 2, what I am saying is VGS is greater than VTH. Okay. And VGD is equal to VGS. Now tell me, if VGS is greater than VTH, is the channel formed?
Yes.
Yeah, the channel is formed. So let me put the channel like this. The channel is formed nicely over here. Okay, right. Will there be any current flow?
No, because
Why?
there is no potential difference. There is no potential difference.
Excellent, excellent. So I told VGD is equal to VGS. Okay. So what does VGD means? It is a potential difference. So this is nothing but VG minus VD is equal to VG minus VS. Okay. So if I rearrange things, what do I have? Okay. 0 minus VD plus VS is equal to 0. Sorry. Or VDS is equal to 0. Okay. So is there any potential difference now between the drain and source terminal? So when I say VGD is equal to VGS, what did it result in? Between drain and source, the voltage is equal to 0. Yes or no? So if VDS is equal to 0, okay, will there be any current flow? What about ID? Because
No
VDS is
current.
No
equal to
current. ID equals
ID, ID equal to 0.
Zero.
Okay. Does that make any sense?
Yes.
Does that make any sense? Okay. Right. So let us move to the next case. Let us move to the next case. Okay. Case 3. So let us take this scenario. My VGS is greater than VTH. Okay. But VGS is greater than VGD. VGS is greater than VGD. Okay. So VGD is also greater than VTH. This is the case that I have now. What about the channel? What about the channel? Is this formed?
Yes.
VGS is greater than VTH. The channel is formed. I am also saying VGS is greater than VGD and VGD is also greater than VTH. Does that make sense? So what I mean to say is VGS is greater than VTH. VGD is also greater than VTH. But I am trying to give a relation between these two also, which is nothing but VGS is greater than VGD and both are greater than VTH. This is the case that I'm trying to solve. Okay, right. So because I told VGS is greater than VGD, okay, so VG minus VS is greater than VG minus VD. Okay, so if I do this and if I take VD to the other side, this becomes VD minus VS greater than 0 or VDS is greater than 0. So what does that mean?
Potential
In this,
difference.
there is a potential difference between drain and source. Will there be any current?
Yes.
Yeah,
Small
so
current.
there will be a drain current. And we will see when we derive the mass current equation, so we will see what is the magnitude of this drain current. Okay, right. Usually I typically give 5 minutes break after 1 hour, but today I think I overstepped. Do you want a small break, 5 minute break? Or shall I do the case? Shall I continue? Right. So anyways, let me finish this case 3 and then we'll take a small 5 minute break. Okay. Now tell me, how will the channel look like? How will the channel look like? Is the channel formed? Is the channel formed?
Yes.
Yes.
Yes, sir.
Okay. So will it look like the same how it looked here? Or will it be some different? Will it look like the same?
No, sir.
No, why not? So I told you VGS is greater than VGD. Okay. Now your channel shape depends on both VGS and VGD actually. Okay. Now I told you VGS is greater than VGD. So what happens is the channel towards the source side, because VGS is greater than VGD, is more pronounced compared to the channel on the drain side. So the channel would look something like this. So the channel is more pronounced here, but as it goes, it becomes a bit thinner. Okay. So this is how the channel would look like. Does that make sense? So the channel shape is a function of both VGS and VGD, and VGS is greater than VTH. So channel is nicely formed here. VGD is also greater than VTH. The channel is also formed here. But I gave you one more condition, which is VGS is greater than VGD. So from this condition, you can say channel is more profound towards the source side compared to the drain side. Okay. Is that clear?
Yes, clear.
Yeah. Also, when I said VGS is greater than VGD is greater than VTH. Okay. So if you solve this inequality, you will see that VDS is less than VGS minus VTH. Okay, so this will directly lead into this. So this is simple arithmetic. So VGS means VG minus VS. VGD means VG minus VD. So substitute this and do this particular thing, you will end up with this condition. Okay, so VDS will be less than VGS minus VTH. Okay, so what are the two main conditions over here? VGS is greater than VTH and VDS is less than VGS minus VTH. See, this is same as writing VGS greater than VGD greater than VTH. These two are the same, both one and the same. Okay. Now, okay. So let us get to case 4. Okay. Right. So what is going to be my case 4? Okay. So I am saying VGS is greater than VTH, but VGD is less than VTH. Okay. Right. So will there be a channel? Tell me. Will the channel be there? Yeah.
No, sir.
So what is this suggesting? VGS on the source side, it is greater than VTH. That means there has to be channel on the source side. Yes or no?
Yes.
Yes.
In the previous diagram, we have seen, right? The channel is not a perfect cuboid. It is more like a trapezium. So if you see here, it is more or less like a rectangle. But in this case, it is more or less looking like a trapezium because of VGS and VGD. Okay. Right now, what I'm saying is VGS is greater than VTH. Because of this, there is a channel on the source side. But what about it on the drain side? What about it on the drain side? VGD is less than VTH. So on the drain side, there is no channel. Okay, so what is this condition called as? So your channel actually stops over here. So there is no inversion that is occurring on the drain side. Okay, so what is this condition called as?
Pinch off.
Pinch off, pinch off.
This condition is called as pinch off. Okay, and the MOSFET is in which region?
Cut off.
It is in actually
Sir.
called in saturation region. Okay, anyways, I'll summarize this later. I think it was too early to invoke this region. Anyways, let me erase this. Sorry for creating confusion. Yeah, so if you arrange these two mathematically, what you will see is VDS is greater than VGS minus VTH. Okay, and the pinch off of the channel actually occurs when VGD is barely equal to VTH and it is in downward trend. Okay, so the pinch off condition is VDS is equal to VGS minus VTH. Okay, the channel is barely formed. Okay, so your channel might look like this. So yeah, your channel might look something like this. So this is called the exact pinch off condition when VGD is equal to VTH. But when VGD is becoming less than, more and more less than VTH, what happens is something like this. See, the channel is there on the source side and on the drain side, there is no channel. Okay. And the point at which the channel stops forming on the drain side, that is called as the pinch off condition. Okay, so this exact scenario is called as the pinch off condition. Okay, right. And because VDS is there, I do have ID over here. So if we summarize all these cases, what do we have? When VGS is less than VTH, ID is equal to 0. This is called the cutoff region. Okay. And VGS is greater than VTH and VDS is less than VGS minus VTH. Or this condition can also be written as VGS greater than VGD greater than VTH. Both are same. So in this situation, we say that the MOSFET is in linear region, triode region, unsaturated region. Depends on the textbook, which textbook you follow. So Professor Razavi usually calls it as triode region. but typically most of the other textbooks call it as linear region. Okay. Then there is one more condition. VGS is greater than VTH. VGD is less than VTH. This VGD is less than VTH. If you follow arithmetic, you can see that this is nothing but VDS is greater than VGS minus VTH. So in this condition, okay, there is no channel towards the drain side, okay, but still there is current. There is ID still. Okay, so here also ID is a finite value. Here also ID is a finite value. You might argue when there is no channel over here, why is the current flowing even after pinch off? Okay, so the current flows even after pinch off. In semiconductors, current flows because of two mechanisms. One is drift, the other is diffusion. Okay, again, if you go into semiconductor physics, you'll be studying these two. So drift is because of the electric field that is present, and diffusion is nothing but the concentration gradient. Okay, right. So if you want me to give a simple example for diffusion, so if you take a glass of water and introduce an a small drop of ink, what happens to the ink? What happens to the ink?
Diffuse.
Yeah, it
It will
slowly
dissolve.
diffuses. Yeah, it will dissolve or diffuse, right? It will slowly go into the water that is present. So that is nothing but diffusion. So in semiconductor, the charges move either because of drift or diffusion. And this diffusion occurs because of the concentration gradient. So this is the boundary. And at this boundary, okay, the concentration of the ink is very small compared to the concentration of water. So because of the difference in concentration of these two materials, diffusion is occurring. Similarly, in semiconductors also, if you take a boundary and at this boundary, there is a very large concentration of electrons on one side, very small concentration of holes on one side. So it is bound to happen. The diffusion is bound to happen. And then again, the flow of electrons or the charge carriers also happens because of drift. And drift is nothing but it happens because of the electrostatic force that is given out by electric field. Okay. So when I said the channel is pinched off, do I still, because of VDS, do I still have this electric field, lateral electric field? Yes or no? Do I still have the lateral electric field?
Yes.
Yes.
Okay. When there is an electric field, which mechanism comes into picture? Drift or diffusion?
Drift.
Drift comes into
Drift.
picture and electrons still cross over from source to drain, which results in a drain current from drain to source. Okay. So what happens in the saturation region is no matter the magnitude of VDS, okay, so ID is constant. So ID becomes constant once you go into the pinch off region. That is once your VDS is equal to VGS minus VTH, or it becomes greater than VGS minus VTH, your drain current totally depends on the drift. It is a combination of the drift plus so many other things that are happening. Okay. But if you want to understand it in a simplistic way, what happens after pinch off is even though you increase VDS, if you increase V, you increase an increase in current, right? So, but that doesn't happen in the MOSFET. Why? Because of so many complex things that are happening over here. There is an electric field that is present over here. And even though you increase this VDS, okay, further after it crosses VGS minus VTH, the current does not depend on the magnitude of VDS and it becomes fairly constant. So ID becomes fairly constant over here. Okay. And in linear region or triode region, okay. So your ID and VDS, they form a linear relationship. Okay. So if this is my VDS, if this is my ID, In the linear region, they form a linear relationship. Okay, it is not like some parabola or exponential relationship. It is a linear relationship. As VDS increases, ID increases. That is why it is called as the linear region or the triode region. And when VGS is less than VTH, there is no question of the current itself. So that is why it is called as the cutoff region. Okay, right. Anyways, I think I took the entire time. I couldn't cover the LT spice. Maybe first half of the next class, I will cover LT spice, then quickly go into the second order effects of MOSFET and the transconductance. Okay, so which is nothing but the channel and modulation, body effect, and then the transconductance. And then the first half an hour, we will try to complete LT spice, how to set up the LT spice at our end. So I'll cover that. So today I took more time to explain the handout, else my plan was to cover LT spice as well. Anyways, I would like to stop here. Any doubts?
So this VDS is nothing but your VBS, right?
VBS is 0, right? The body is connected to source. So these two are at the same potential. So VBS is 0. There is no potential difference between bulk and source.
Right.
Uh,
But we don't
okay,
have VDS, right?
in effect, we don't have, but it results in an lateral electric field here. Okay.
Okay.
So, so when I say VGS, this is one voltage source, and VGD, this is another voltage source. Okay.
Right.
If I want to compare these two, this is VG minus VS, this is VG minus VD. So in effect, what do I have? If I rearrange
Okay.
them, I have VD minus VS. So if I am talking about both VGS and VGD, what am I talking about?
VDS.
I am talking about VDS. And this VDS is because of the lateral electric field. So VDS, the potential difference between these two terminals appears as an electric field. And we know that electric field is nothing but VDS divided by length, right?
Yes.
The voltage gradient is nothing but my electric field. And the distance between these two is nothing but my L. Okay, so when I derive the ID current equation, so I'll introduce what is L and what is W. So this MOSFET actually grows into the page, into this paper. Okay, so this MOSFET is actually 3D structure where it actually grows into the paper as well. Okay, like this. And this dimension is called as width. And this dimension, the distance between the source and drain, simplistically speaking, is called as the length of the MOSFET. Okay, slowly when I derive the ID equation. Okay, so next class will be ID equation. So from that GM equation and second order effects, channel length modulation and body effect. And then last half an hour, I will do LT spice. Okay, so this is going to be our next class. Okay, right. Any doubts?
Hello, sir.
Yeah,
Uh, are we going to learn body biasing also? Like
yeah, we'll
applying?
see. Yeah,
Hmm.
we'll see while how do we model the body effect when we do the second order effects. Okay, so in the next class we'll see how do we model that. So we see that GMB also comes into picture. Okay, so from that GM and GMB, okay, anyways, I'll put it here. If I introduce these two terms, I can go to the small signals of the MOSFET as well. Okay, maybe I'll put it for session 3. So small signal model and then single stage amplifiers we can go. So that is for session 3. Yeah. Any doubts you feel? Any like I can speed up or slow down or any type of feedback is most welcome. Okay. Or you want some more explanation of some topics? So you can share the feedback. I can adjust accordingly.
Yeah, one small feedback from my side.
Please.
Sir, actually, when we take a real MOSFET, right, we never apply
Uh,
gate to drain voltage. We generally apply drain to source and gate to source.
yeah, true,
So,
true, true,
right.
true.
So with this method, right, it
Uh,
looks more complicated by learning the equations because
yeah,
gate,
but
yeah,
yeah. So all I wanted to say is the channel shape is a function of VGS and VGD. I know that in circuit analysis, this VGD doesn't come into picture because we don't even apply any voltage sources that you said. You are true. But in order to explain this pinch of condition, I thought this would be more intuitive. Why? Because if you try to divide this into half, so this half of the channel is being governed by VGS and this half of the channel is governed by VGD. So then this pinch off, understanding this pinch off becomes very easy. So that was the thing that I tried. Maybe I should have explained it in a better way. Yeah, but yeah, what you told is right. As a voltage source, we never apply potentials between the gate and drain terminals when we are doing circuits. But my point is, in a very simplistic level, if you divide this channel into two halves, and if you say that this half is being governed by VGS and this half is being governed by VGD, it becomes more intuitive to understanding. That is usually mm, so there is one textbook called Leblacy, Yusuf Leblacy. So in that textbook, this approach is given. Even even Westy Harris follows this approach. So these two textbooks, uh, so take it from this pedagogy level. They say that they argue that channel shape is a function of VGS and VGD. VGS takes care of the left half and VGD takes care of the right half. So in that way, they try to explain the pinch off condition. You might, if we come from the VDS side, it might not be so intuitive to understand. Maybe I should have done better. Yeah, that was the logic behind going ahead with VGS and VGD. Yeah,
So, sir, if we don't have VGD, VCS, we only have single source. Um,
uh,
like we try
so
to understand it with the voltage difference, right? So
see,
what? Huh.
you cannot say that we don't have VGD. So if you have VGS and VDS, you are already speaking about VGD. What the other person was trying to say is in circuits, this doesn't predominantly come into picture. It is always present. It is not like there is no VGD. The MOSFET symbol is like this now. This
Yeah,
is
yeah.
my source, drain, and gate. So there is
Okay.
potential difference between these two. So I have
Mm-hmm.
VGD. Mm. Typically,
Okay.
in MOSFETs, the drain current is plotted here, and
Mm-hmm.
typically it is given as all the textbooks give it as a function of VGS and VDS. Okay, so that is the reason that the other student was referring to. But if there is a potential difference between gate and drain terminals, VGD is always present between these two. Okay.
Okay. Okay. Okay.
Hmm.
Got it.
So when we derive the current equation, it becomes more clear what the other student was trying to convey. Okay.
Okay. Got it.
Yeah.
Sir, I have one question. So,
Yeah.
after certain point of time, even though we increases that voltage between drain and source,
Yeah.
current will be saturated. Like what you
Ah,
said. That's okay.
yeah.
That's okay. Understood. But
Uh,
so
uh,
basically, if you take some electric field based scenarios like antennas and mobile phones, so when we increase that intensity of that electric field, so we can expect some more and more kind of signal
See,
strength like that. No?
yeah,
So
it is a very simplistic explanation, and what I told is only maybe applicable to long channel devices. Okay. And MOSFET is a three-dimensional structure, and it is a very complex, what do you say, complex physics that goes behind it. Okay. See, see, this is an N-type semiconductor. This is P-type semiconductor, right? So
Yes.
now, can I say that there is a diode forming between these two?
Yeah, we can say.
So this P sub is connected to ground, so this is grounded, and this N type is connected to a positive voltage. Yes or no? VDS. When I'm talking about VDS, drain is the positive voltage. So this is
Yeah, yeah.
connected to some VD. Yes or no? A positive voltage. So what
Yes.
bias will be this one?
Reverse.
So this is in reverse bias. When there is a reverse bias, okay. So let me put it this way. Yeah. When there is a reverse bias, what happens? There will be a depletion region between N and P. See, this is N and P semiconductor. Okay. So if you put reverse bias, there will be a bigger depletion region, yes or no?
Yeah, yeah.
Okay. So the same thing happens here also. There will be some bigger depletion region here also. Okay. And that too, see, this is P type, this is N plus. Okay. So the depletion region will be very thin on the N plus side, and it will be bigger on the nominally doped side. Okay. So the width of the depletion region again is a function of the concentration of this N region and P region. Again, this comes in semiconductor physics. So if this is heavily doped, the depletion region width is somewhat lesser here compared to the depletion region width on the nominally doped side.
Yes. Chips,
Okay. So
moreover, lessly doped.
yeah, so if it is equally doped, then these widths are equal. WP it will be equal to WN. But if it is heavily doped, it will be very thin on the inside and will be very high. So this depletion region also eats into the channel, yes or no? This depletion region consists of immobile ions, right? The
Yeah, yeah.
depletion region. So there is no charge conduction that is happening over here. So what we are trying to give is a very simplistic picture. So what is happening behind is there is an electric field that is present, and as you are trying to give more and more negative charge, there is this depletion region that is also eating into it. So whatever may be, like you told, as I increase the electric field, the charges should increase. Okay, in the same order, this depletion region might be reducing those, and both effects are canceling out, and in effect, I have the same saturation current. So you get the picture what I'm trying to give it. So it is not only one phenomenon that is going on. Okay, at the same time, so many things are happening. What I told is a very simplistic explanation of the saturation current being very low. Like you told, more and more electric fields should attract more and more current. But as I increase this voltage, this depletion region width is also growing, and this may be one of the reasons why that the saturation current is not increasing so much, even though I am increasing the voltage. This may be one of the reasons. Yeah.
So maybe technological parameters also differentiate.
Yeah. Yeah. And if it is a very short channel device, sometimes this depletion region width might eat out into the entire channel as well. Okay. So there are so many second order effects. Okay. So channel length modulation and body effect, these we have to study. Okay. Um, Other than that, we do have DIBBLE, drain-induced barrier lowering. Okay, and so many second order effects. SIBBLE. Okay, at least some 10 to 15 phenomenon are there that usually textbooks discuss, but we don't know what goes into unless you are a physicist working in the clean room. Okay, so they give you the model file, right? They might be doing the curve fitting for at least 200 parameters. At least the modern FinFETs are short channels. Okay, so many parameters and so many variables are there. Okay, and we are trying to get a very simplistic view of those things.
Yeah, understood.
Yeah, yeah, I think we are almost there. Okay. So I'll upload this PDF. I'll convert this to PDF, and whatever are the first week slides, I'll upload those as well by tomorrow. Anything else that students have doubts on topic wise or course wise?
No, thank you for explanation.
Yeah, thank
It was very clear actually. So when will be our next class on this topic?
Same, right? Every Sunday, 8:20.
Every Saturday. Okay.
Sorry, every Saturday. Sorry. Every Saturday,
So
8:20
so in
morning.
the next session, we are going to talk about LT spice setup and all, right?
Yeah. I wish to. Anyways, I plan to cover these. Like I told, ID derivation. So GM and GMB, channel and modulation, body effect. I'll complete these first. And then last half an hour, 40 minutes, we will go ahead with LT spice.
Okay. So any plans on discussion about the channel and its importance?
Which one? Sorry.
The channel
I-
channel length.
Yeah, when we discuss about ID, the length and width,
Yeah.
of course, they come into picture. So I'll introduce
Sure.
length and width. Yeah, when we were
Sure.
discussing it. Okay.
Thank you so much. Thank you. It was very informative session. Thank you.
Yeah, thank you.
And so when will the recording be available? Is it immediately?
Immediately, once I close this session, the recording will be available here in the shared. So in this tab, another recordings folder will open up, and you can see the recording over there.
Okay. Yeah, thank you.
Okay, thank you. I think you have your next class. We will end it here. Thank you. Thank you all for joining. Thank you.
Thank you, sir.
Thank you.
Thank you, sir. Thank you.
Thank you.
Thank you.